Hello. After studying previous lectures, you must have become familiar with Maxwell's equations. In this lecture, we shall discuss the solutions of Maxwell's equations in different mediums. These are the Maxwell's equations in differential form and in integral forms. The first one is the Gauss law. Second represents that there is no magnetic monopoles in the nature. Third is the Faraday's law. And fourth is modified Ampere's law. We already know that provided the field vanishes far from its source, the curl and divergence of it are sufficient to determine that field at any point of question. Let us find how. Let us find the solutions of Maxwell's equations in free space or in the vacuum. The free space is defined by zero current density and zero charge density. Applying these definitions of free space, the Maxwell's equations get this form in free space. The problem in electromagnetism is to determine the electric field and magnetic field at any point in space at a given instant of time. It means that there is two unknowns. To find them, we have four equations. So, we need to reduce four equations into two. To do that, let us take curl of third Maxwell equation, which can be solved using differential identity with Laplacian of the field and by putting value of curl of B from fourth Maxwell equation. Here we again reversed the order of derivatives with respect to space and time. Since the gradient of divergence of a vector field is 0 always, it reduces to this. This equation contains only the electric field as a variable and can be solved to find it. In similar way, you can find the equation for magnetic field induction B also, like this, this, and this. At this point, we have two equations for B and for E. These are second order differential equations for electric field and magnetic field induction. Let us discuss what conclusions do these equations provide. Firstly, in free space, electric field and magnetic field induction vary in form of waves. How? Equations with double derivative terms with respect to time and with respect to space represent a wave. A general form of equation representing variation of a variable y in space and time as a wave is this. Here, v is the velocity of the wave. Since electric field and magnetic field in these equations vary in the form of a wave, they represent a wave and their velocities are also the same. So, one can conclude that E and B waves propagate in space with each other and this type of waves are known as electromagnetic wave. Secondly, to find the solutions, we need not to solve E and B equations analytically because we know that the solutions are in form of wave. The solutions can be written as these, which are the wave solutions. Here, E0 and B0 are the complex quantities and the physical fields are the real part of E and B as a function of position and time. And K is known as wave propagation vector given by this. The direction of K vector is along the propagation of electromagnetic wave. Let us find the velocity of this electromagnetic wave since we have the values of the coefficients epsilon naught and mu naught. This comes out to be the velocity of light 3 into 10 to the power 8 meter per second. By this, one can conclude that light is an electromagnetic wave. Now, to find the relationship of E and B, put the solutions of E and B in Maxwell equations. Let us put solutions of E and B in first and second equations respectively for a start. Before proceeding further, simplify the equations by expanding K and E0 into their components like this. By this, E and B wave equations take this simplified form. So, the E equation is solved like this and this, which gives this result. Similarly, for magnetic field induction, we get the solution this. The conclusion is that E and B both are perpendicular to K or propagation of electromagnetic wave. Now we know that in an electromagnetic wave, electric field and magnetic field vary perpendicular to its propagation. Now put E and B solutions in third and fourth Maxwell equations. This can be done like this, which you can do by yourself to have K cross E equal to omega times magnetic field induction. This is the result by putting E equation in third equation. Similarly, if you put solution for magnetic field induction in fourth Maxwell equation, you will get this. So, in an electromagnetic wave, E, B and K are mutually perpendicular. So, we are in condition to picturize electromagnetic wave. So, this is an electromagnetic wave. Its K vector is along positive y-axis and E and B vectors are vibrating in direction of z-axis and x-axis respectively. These are the Maxwell's equations in free space. These are the solutions of electric field and magnetic field induction which have the form of wave in free space, and these are the solutions of electric field and magnetic field in wave form, where K is wave propagation vector and E0 and B0 can be represented in their component forms. We have also found the relationship between E0, B0 and K. In that, the relation between K, E and B was found by placing E and B solutions in Maxwell's equations, and that gave the conclusion E and B are perpendicular to wave propagation vector. We have also found this relation by putting these solutions of E and B in third and fourth Maxwell equations, and its conclusion is that B, E and K all are mutually perpendicular. While dealing with Maxwell's equations, we can always put these two approximations of dial operator and differential operator with respect to time. If you see this equation, this can be used to find the relative values of electric field and magnetic field induction. Since E, B and K are mutually perpendicular, if we represent this in its magnitude form, then it will be K multiplied by E equal to omega multiplied by B. So electric field will be omega by K multiplied by B, which is equal to C into B, where C is the velocity of light in vacuum and is equal to 1 by under root of mu naught epsilon naught. So this is further reduction of this equation. The magnetic field induction and the magnetic field intensity H are related with this equation. So if we replace magnetic field induction B by mu naught into H, we get the ratio between E and H will be under root of mu naught upon epsilon naught. The value of this is 377 ohm. This quantity is known as wave impedance of free space. It is also called intrinsic impedance of EM wave, and in a way it gives us liberty to do majority of EM wave analysis in terms of electric field vector only. We can do this whole practice for a dielectric medium also. A dielectric medium is also defined by vanishing charge density and current density. The only difference between free space and dielectric medium is in the value of coefficient epsilon and mu. For a dielectric medium, epsilon naught and mu naught are replaced by epsilon and mu, values of which can be found by multiplying the respective terms with the relative terms epsilon r and mu r. Epsilon r is known as relative permittivity of the medium and mu r is known as relative permeability of the medium. Now the Maxwell's equations become these. The only difference is in the coefficient. So all the treatment will be the same. We will get wave equations for electric field and for magnetic field induction. We will have the velocity of electromagnetic wave in dielectric medium, and this velocity will be the velocity of electromagnetic wave in free space divided by the under root of multiplication of relative coefficients. So this is the only difference between dielectric medium and free space in electromagnetism. So, as a conclusion, the velocity of electromagnetic wave in a dielectric medium is less than the velocity of electromagnetic wave in vacuum. And the ratio of these velocities is known as refractive index of the medium, which will always be greater than 1 because epsilon r is always greater than 1 for any medium, and mu r may be equal to 1 for a non-magnetic material. In the next lecture, we shall try to solve Maxwell equations for a conducting medium.